Okay, in this video and the ones that will precede it, just a few, I want to talk about the issue of going to Mars. And I'm not talking about going to Mars in terms of people. Yes, I would like to go, and there's some efforts to get us there maybe in the next 50 years or so. But we have gone to Mars in the form of, in the past, about 50 robotic missions. And I'll say when we have actually landed on the surface. Okay, so we have launched robots, usually in terms of little buggies and cars, in rockets, and have landed on Mars. And that's what I'd like to talk about a little bit, because getting to Mars is a very, very hard. Okay, so the planet is always in our focus. It's close to the Earth. It's the easiest one to get to. Um, Setting Venus aside, of course, no one just wants to go there because it's so hot. Mars seems like the best one to try to go to, but of course, as we know, there's many problems with Mars. And what I'd like to talk about then is some of the considerations about why it's so hard going to Mars from an engineering standpoint, because it also highlights some properties of the planet itself. I mean, the planet itself make it hard to land on, and I'd like to tell you why in this video and the ones that have come up. In the first case here, I wanted to tell you a little bit about just launching rockets. And I'll show you some images in a second, but just one of the considerations here. Okay, so suppose you weren't even trying to get to Mars, but you're just trying to put something in orbit around the Earth, which is mostly what we do with our rocket launches and things like that. Well, it turns out that, as you know, if you want to get something to orbit Earth, you have to reach that balance. You have to reach the orbit. Remember, we had a few videos on it a while back. The balance between the speed, which we call v or velocity, and F sub g, which is the force of gravity. So if you have a little satellite like this that you're trying to get into orbit, remember that you have to have its speed sort of maybe going in a direction like this. There's its speed, and you have to have it sort of balance the downwards pull of the Earth's gravity. So let's just look a little more carefully at this issue here, because I want a number to pop out that I'll show you. So as you sort of recall then, the force due to gravity is a constant, gravitational constant, times the mass of the planet, times the mass maybe the satellite, divided by the distance squared. We sort of saw that formula come up a few times. And the two masses involved, I think in the past it was called M1 and M2, but here I'll call it mass of the planet and mass of the satellite, because those are the two objects that we're sort of concerned with here. Here's the Earth as a planet, there's the satellite right there. Those are the two things that we're concerned with. So if you have a satellite like this, and you want to sort of put it in orbit around the Earth, let me just plug in a few numbers and show you what sort of happens here, okay? So this is sort of one consideration right here. And the other consideration is that when your satellite is going in a circle like this, which is its orbit, something called the centrifugal force is always going to pull it outwards. And we sort of saw that in past videos when we were talking about how the solar system formed and maybe how our moon formed for a theory that didn't hold up. But we'll just sort of label that centrifugal force here. And once again, I'm always obliged to put a little star next to this here, because for the purists and people who might be watching this video here, I know the centrifugal force is not real, but it serves us very well to get our point across in this video. So if you look then at these two arrows here, the centrifugal force is always out, the force of gravity is always down, and you reach orbit, of course, when they balance. So just like we have an equation for the force of gravity, we also have one for the centrifugal force. I'll label it F sub c, F sub centrifugal. It'll just be mv squared over r. Or let me not call it r because we're using d, it looks like, so let me just call it d right here. So gravity, of course, involves the mass of the planet and the mass of the satellite. The centrifugal force involves the mass of the satellite also. Let's put m sub satellite in there. And now finally, see, we have a reference to that velocity in there, and of course its distance. So when you get an orbit, you can definitely write for sure that the gravity is going to balance the centrifugal force. This is that balance that were referred to in past videos between gravity and the speed. That's the balance that we're talking about. So indeed, we can equate the two equations, g times the mass of the planet times the mass of the satellite divided by d squared. All that's equal to mass of the satellite times v squared over d. Yeah, okay. So this is the balance that we're talking about in here, okay? And so what happens now is just a little bit of math has to happen, no big deal. We can cancel out the mass of the satellite. So indeed, it doesn't matter how heavy your satellite is. That doesn't matter for the balance that you're trying to strike. And also, because there's a d here and a d squared over here, you can get a little bit of cancellation. That d will cancel just one of those. And so if you rewrite the whole thing, it can be written as g times the mass of the planet over d is equal to v squared. And you can solve for the speed that you would need to pull this off. It'll be g times the mass of the planet divided by d, the distance between them. So see, you get a little equation here that tells you, well, what speed do you need to obtain to get your orbit? To be in an orbit of height d. That's what the equation tells us. So finally, we see a little equation that tells you what the speed should be, and I will tell you about it in the next video.